Welcome to Foss-North 2020, a virtual event. I'd like to thank our sponsors and our partners. Welcome.
Good morning, good evening, good afternoon. Let's talk about Secure Boot today. And let's talk about teas, but not teas to drink, something a little bit different. My name is Marta and I have been developing open source for the last 20 years and something like 15 years in embedded. I have background in security and that's why I'm doing this deep dive for you today. In addition to security, I've been working in both product development and silicon, and you will see that it allows me to cover that subject in a pretty specific way. I've been contributing to the Eclipse Oniro distribution since 2021, and we are going to cover Secure Boot and Oniro in this talk. Why? Why to talk about Secure Boot? I find that there are three main reasons, three main doubts people have about Secure Boot. First is the confusion. Confusion of people who are not directly working with the Secure Boot technologies. The reason for that is that there are quite many abbreviations, different technologies from different vendors, and it could be somewhat complicated to figure out which solution is which when you are not following it directly. I've been receiving questions from developers like, what's the difference between the trust zone and the SCV? I've been also having questions about the different software projects like TFA and TFM. What's the difference between the two? We are going to cover that into this talk. Then the other doubt regarding to the Secure Boot is the mistrust of community. The mistrust related to fear of lockdown platforms. I find that there are two directions of this fear. One is the fear of a user, the fear of having a lockdown platform that you are unable to control anymore. And then there is the second fear of a developer who have to use some specific solutions for whom it will be more complicated to develop on the development platform or on the product platform they have. And then the third issue is the perceived added complexity. Secure Boot adds additional steps into the boot process, and it means it's harder to run such a system and it's harder to modify such a system. We at Oniro, we are doing a distribution for embedded and IoT. What makes it even more interesting in that context is that we are running multiple operating systems. Apart from Linux, we have Zephyr and others. And we are also running various hardware platforms, both small and big, and using different processor architectures. It means that we are pretty interested in all unified approaches, the ways that allow to use different technologies in the same way, because it makes our maintenance way easier. All opinions in this talk are my own. I'm simplifying a quite many things also. So if you are interested in discussing the details, we can do it in the question sections, or we can discuss it offline after the talk. Now, there's one more introduction subject to cover. Why would you want secure boot? And here again, the opinions are my own. I would like to be able to detect if device is running the software I expect it to run. The software I expect it to run means no rootkits, no malware, but also no debug version that have been flashed in a production device by some kind of an accident. And then making sure the device is running software under control. Either device flashed by someone else or the device I flash. So it's under control, trusting the people have prepared the software. Trusting that they control all the components they have built into the system. When we come to updates, I like to have verified images. Verified images meaning that we know where the image comes from, if it's the right image, if it's the right image in terms of the software it contains, for example, more up-to-date than the image that we have, and also the right one in the matter of for the right product. In some use cases, we want to have encrypted either the whole system image or the file system, if it makes sense for the use case, and the data that we process in the device. When we are looking into systems that could be running secure boot and all the systems we run in practice, let's look into the history of how the technology has been evolving. And the big questions we have, while the most important question is, whom do you trust? And let's cover two examples. The example of a generic PC, an example of an embedded system. Now, a generic PC can be represented as on this image. You do have the hardware, the processor that is running the operating system and applications. The processor itself is something that you trust to separate the operating system from the applications, and that we trust to separate applications one from each other. The processor has a few hardware elements to perform that work, like the memory management unit, MMU, or the kernel links. In this case, we usually trust the operating system kernel because it is running a big part of the protection between the applications. It's using the hardware, but it's really implementing a big part of the protection. And then the applications are generally untrusted. They can be running, trying to do things that try to bypass the security measures that we have set. And it's a little bit different in a traditional embedded system. In a traditional embedded system, we do not have an MMU. Quite often we have an MPU as an option. And in this case, applications and the operating system were all linked together. All linked together and also running from the same memory space. That means that this application could access data of different applications, maybe even of the operating system, could modify it depending if the MPU is set up or not, and if it's present in the specific system. This typical embedded system is running simple applications. And our trust on the whole product depends on heavy debugging, finding out in practice that the solution is working correctly, and analysis of the source code. But in addition, we trust it just because we really do not have another choice. Secure boot in this situation, it's a pretty complicated thing. Basically, we do not have secure boot. The boot process is insecure. You may be having an additional step, additional software running in the middle of the boot process, adding something, installing, monitoring software, modifying the way the hardware is behaving. Basically, malicious software could access the whole memory, overwrite everything, and if there are cryptographic keys in the system, quite often accessing them. So there have been some technologies to being added so that we can add some more protection to the system. The first that has shown up is the TPM, Trusted Platform Module. It is two things at the same time: a security cryptoprocessor and a standard. It has shown up in the news around 2007. A TPM can be a separate chip, and that is a big majority of the cases today, but it can be also a part of the chip. It can be in firmware, and it can be in software. There exists software projects to actually implement a TPM and emulate the TPM. The main use case for the TPM was system integrity. But you also have other functionalities, like there's typically a random number generator, or in some cases, acceleration for crypto algorithms. And of course, I provide you a few links if you're interested to read more. In a system with a TPM, we are mostly in a situation of the general purpose system that we have seen before. And we add one more block, the TPM. The TPM can encrypt and decrypt keys, but it's quite limited because it cannot typically it doesn't have DMA access. It means that it cannot access memory on its own. It means it cannot read the memory to verify it. It depends on the operating system and the drivers to fit it with data. It means, in my understanding, that the operating system needs to be trusted so that you can trust it to fill the TPM with the right data, or not just bypass things that it should be passing to the TPM. And then, in the other part of the spectrum of the hardware platforms, we have Ts. T means Trusted Execution Environment, and it's typically a part of a processor. A part of a processor that protects loaded code and data in terms of integrity and confidentiality. Mostly integrity. And there are different implementations also, like the same as with TPMs. there exists a specification from global platform, an API, but this specification itself is not it is not open source. You require a license to access it. And then we do have OPTEE, Open Portable Trusted Execution Environment, which is an implementation of T, this time as open source, for typically ARM processors with trust. And OPTEE is working with Linux as the main operating system. Now, how our diagram looks like in the case of an ARM style T. From the trust in this case. On the right hand side, we have the non-secure mode, which is basically what you know from the generic system. And on the left hand side, you have a duplication of that called secure mode. You also have the kernel mode, they have the user mode, you have the operating system running in the secure mode that is separate from the generic operating system. You have applications running in the secure mode that are different from the applications running in the non-trusted mode. And the process has a functionality to support those two modes and to create separation between them two. Now, let's come back to the comparison between the TPMs and Ts. They both contain crypto accelerators, typically, but there are quite many differences. TPM is typically a separate chip. T is inside of the main processor chip. TPM has it's functionally hard-coded. It can do some operations it has been programmed to, and typically you cannot change those operations. On the other hand, in Ts, you can run applications into Ts, so you can change the code. And TPM typically has pretty small storage. In the case of Ts, you either have a big storage or you have access to a separate storage attached to the secure world. There are quite many differences. And then the T model is incomplete without one more element. Those days, hardware is not totally only hardware. You have hardware and software running on this hardware called firmware. And this firmware typically comes from the vendor. Quite often it has been closed source. It does some low-level interactions with the hardware itself. For the ARM side, we do have two projects, TFA and TFM, Trusted Firmware A and Trusted Firmware M, to reference implementation of firmware as open source for the A series of ARM processor and the M series platforms. And TFA is expected to work next to OPTEE and supply it with the hardware operations. Of course, as for any operating system, any open source project, there's documentation that you can look into and see the details of the implementation and how it works. Now, let's switch platforms to the Intel platform. It has SGX solutions in different versions also, so I'm simplifying a bit. SGX allows to create a specific memory region called an enclave. This enclave is a memory zone that is separate from the operating system kernel, and only code from the enclave can read and write it. The memory could be encrypted in addition. It's a kind of a separate place that you can run your code from. If you are more if you'd like to learn more, there are some articles that you can look into. And then we have SEV, Secure Encrypted Virtualization for ARM, which is a similar thing, but on the AMD side. It adds encrypted memory for a virtual machine. Keys are handled in the firmware in this case. As in the case of the Intel solution, the host cannot access the memory space. Pretty similar, with the difference that it's really related to virtual machines. Now, we compare the trust zone, SGV and SEV. The similarity is that all of them can be used to create a tree-like design that separate part of memory when you can run some code. But in the case of SGX, SEV, they are designed to run mostly for virtual machines, and they do not have a separate crypto accelerator. In the case of a trust zone, you can access some peripherals when on the other side you just have the memory. Another difference is that in trust zone you have only one secure world and the other non-secure zone. So you can run one instance of the securest and one instance of the non-securest, while on the SGX SEV case, you can run multiple enclaves with different applications and different copies of the operating system. Now, related to that is the confidential computing initiative. The definition comes from the confidential computing group. They are aiming at protecting data in use by using hardware-based keys. And by hardware-based keys, they understand mostly the enclave type hardware platform. Their main focus is sensitive data like in medical or financial, quite related to data protection regulations. As they are protecting the data in use, they are assuming that the user already has existing solutions for the data transit and data storage that we probably all know about. If you are more interested, there's pretty nice webinar that you can watch to learn more. Now, if we try to summarize all of it together in this trusted or confidential computing world, we have the processor hardware we're expected to trust, creating a boundary using the known technology that again standard like MMU or IOM. We have the standard as before operating system and applications, but you also have the other part, the trusted secure part, running a secure OS kernel or a library OS in secure mode. And we have the applications written to use that operating system, separated from the general case operating system and applications. And confidential computing is focusing on that application part mostly. Now, what I've been noticing here that we have a little bit of a gap between embedded and cloud. We have quite a similar solutions for different architectures, for the embedded pod and for the cloud pod, but they are different ecosystems. And also, apart from different ecosystems, we have different hardware limitations. We have listed some of them, having just one secure mode versus having multiple ones. And that leads to a problem that currently I'm not aware of a platform that allows you to write one application, do one design, and run it on every platform of different technologies. Attempts to that exist, and there's work in progress, for example, in the OpenEnclave SDK, but still it's not there yet. In addition, we have fragmentation. On the embedded side, we have vendor BSPs delivering different versions of software, delivering different versions of bootloaders, the kernel, OPTEE, and other related libraries. On the cloud side, we have mostly different architectures and different versions of processors with the various extensions and quite many different versions of the security extensions. So we have multiple architectures that are showing up or that are existing in the hardware you have. So how would you link it all? Secure boot and teas and enclaves. There's a lot of focus on applications, but what if an attacker can modify the runtime that's running your secure application? What if an attacker modifies the bootloader running your software? If it can happen, it means that it can run some software that will be emulating for this secure application. Will be emulating the fact that the application is expecting to be running into the secure, but it's not. And this malicious runtime could be trying to get data, get keys, get privacy-related information from the application. So, in practice, if you are running a T-related design, you should be running a secure boot to be sure that you can assure that the attacker cannot inject an element into the boot to actually cancel all the security solutions they have put in place. Now, in the Oniro use case, we have talked about the fact that we are aiming at unification. A part of that is using UFI boot on x86 and ABBA for ARM. Why is it so? It is because ABBA simplifies UFI, so it means that we are getting two platforms to the same direction. Behind the scenes, the ABBA compatible implementation is using OPTEE to store UFI variables in a secure place. This works thanks to Linaro. A complete root of trust, another thing to do, are based at first. And here we are really running into changes about unification of the BSPs from different platforms. And then we do not have yet a one framework to run applications from different vendors. So we have at this point to offer different frameworks for different platforms. There is some work you can do right now. If you care about making all those technologies easier for everyone to use, prefer open source solutions for software and standards. If you are communicating with vendors, ask them when the patches are going to be upstreamed. If we get a patch upstreamed for different BSPs, different platforms, it'd be easier to build solutions that work on every platform and support unification's efforts. Try them out, submit patches, submit feedback. And it's true that sometimes unification can be a little bit more complex, but the advantage is that you'll be able to run your applications on different platforms with the same code instead of writing different applications for different platforms. A few links to the Oniro project, the project itself, and the project on Eclipse, our source code with the work we are doing on the secure boot. Thank you for following this talk. I hope that you have learned about some of the abbreviations that maybe you haven't known before, that you have learned a little bit about the terms, about the use cases, and what we are trusting and what we are not trusting in this case. The journey doesn't end up here, not at all. I haven't talked about the hardware limitations, the hardware vulnerabilities. Yes, because there are some. And I haven't talked about what is coming next, or the other projects that are creating unification's effort, the new features that they are coming. I think we are in an interesting place for the development on privacy-related and secure-related projects, because the technologies are showing up. We can use them to protect user privacy. We can use them to protect sensitive data. And if you are dealing with sensitive data, you are probably going to use one of the technologies sooner or later. I hope this introduction has been useful. If you have any comments, you have any discussion topics, do not hesitate to ask the questions right now or catch me after the talk. Thank you.
So yes, let's see if there are any brave ones here. Otherwise, I have a question that I could start with. It's about the implementation of the open source teas in comparison to the standards. Is that one of the ways to sort of figure out the APIs? I know, for instance, that the Linux kernel refers to the POSIX standard, even though the POSIX standard at least used to be closed.
What we can see is that most people start from the source code, from the OPTEE and its examples as a base of the work. There are not so many people apart from some security searchers who actually read the specification. So people take the source code and that is their base, and that's how they are working. So yeah, it's pretty similar.
So extending the project rather than rewriting. I see that there is one person typing on and off Ipa Karin. I'm waiting for a question there. There we go. So, do you think TPM and cryptoprocessors have the potential to threaten open computing? In theory, they could aid vendors in building even more closed application stacks than just obfuscated and difficult to reverse engineer.
This is a very good question. And this is to send out the same fear people had like 10 years ago when the TPM solution starting to appear. The fear was exactly that those technologies will take away the user's freedom to install what they want, especially in our case, install open source on the PCs. As we are a little bit more in the future and we know what happened, that didn't materialize. There are some use cases that have become a little bit more complicated. In some cases, you have to disable an option in the BIOS, but in most cases still, the user has an option to use their own key called the machine owner's key, typically. And then they can use the device as they wish. There are certain use cases when I personally find that it's good to block the easy way of modifying device. For example, if you're running a medical device, especially if someone's life depends on it, it's good to block any possible modification, put some strong verifications if you really want to change the software on this device. Another important factor, I think, is that since the introduction of TPMs in the early 2000s, the environment had changed and open source became even more popular. Most of the products today are based on open source. It means that if vendors want to block the open source solutions, they will disable the possibility to build products based on the device. So I do not really think it's going to happen. But still, the risk is there. The theoretical possibility is there, and it's up to the open source community and users to have a pressure on vendors to make sure they know that allowing to run open source software with those technologies is an important point for the users, and they will that will be a factor for their buying decisions, basically.
I see that Epa Karim is writing again, so I'm checking if there's a follow-up. I guess you also see the typing going on. And then we have Nico typing something, so let's catch that one. Do you think user control regarding these keys could be handled by legislation? I remember when phones would be SIM-locked for certain carriers and you could get them unlocked for general use. Perhaps something similar can be done around keys.
From a legislation point of view, I think it would be better to ask our Free Software Foundation Europe friends, because they know this subject way better than I do. But from the technical point of view, the technologies, or the software related to allowing user to have their own key, they exist. And they can be used by the vendors if they wish to.
Good point. And then we are using FSFE's infrastructure here, so I think there are representatives here that can bring it forward. Do we have more questions coming up? Start typing now or raise your hand, please. Going once, going twice. Then I'd like to thank you very much, Marta. Very enjoyable talk. I have automotive background, so I recognized a lot of the topics. It's a very interesting topic in trying to ship devices to end users and still fulfill legal requirements while being open. It's a tricky scenario, definitely. But thank you very much.